Right. Good morning. Any questions? Any comments? So I want to go through a problem from your book, but I'll modify it with my tastes. So if you want the original, go to book and do it on your own. So this is problem 2.19. Okay, I'm not going to give you this statement of the problem, but I will explain you the physics. So first, I want to think about a box potential like this. And suppose this is the center of the box. And this is minus A. So this is A. But different from the infinite box, I don't want to consider infinite box. So here I want to consider there are no walls. Okay? This is a little bit different. But I want to say, okay, what is this? Okay, V again is 0 inside. And we know the solution of Schrödinger equation, but I have to impose boundary conditions. And the boundary condition I want to impose is psi of x is equal to psi of x plus 2a. So this is what I call periodic boundaries. So there are different ways to look at the problem. That's how I think about this. So that means if you take any point here, and if you translate like this, you should have the periodicity. And what are the solutions? The solutions are A sine kx and something like, let me call it V cosine kx. And these are like odd solutions with respect to center of the domain. And this is even solutions. And from the condition of periodicity, right, I want to have, like, for example, sine kx is equal to sine kx plus k times 2a. And that is going to give me k times 2a is equal to n times 2 pi. That means k is equal to pi over a times n. Then any function, so any function in domain minus a to a. So any function, we know, like mathematicians, they are going to find edge cases. We don't care about these edge cases. Reasonable functions are going to do for us. And any function f is going to be written as f of x is equal to and we call this, if you want, let me box that in. So we call this, if you want, Fourier series, and this is Dirichet's theorem. Right? Any function in that domain can be written in terms of sines and cosines. Some people want to write zeros separately, and they want to start from 1, but you know, use your own thing. I'm just copying what the book gave me. This is the expression in the book. Now, what the book is asking is like convert this sine and cosine to exponentials. So let's find an alternative expression for this. So what I want to do is, so I want to write sine as e to the I n pi over ax minus e to the minus I n pi over ax divided by 2I, and similarly for cosine. So I will write this plus, erase I, and this is for cosine. Then I can write this f of x like n from 0 to infinity. So I am going to collect e to the in and e to the in here. So this is an divided by 2I plus bn divided by 2 times e to the I n pi over a times x plus the second ones minus an divided by 2I plus bn divided by 2 e to the minus I n pi over a x. And now I want to separate, let's separate 0th one. So this is 0th one from here. Okay, this is 0, 1, this is 0, 1. So this is going to be a0 over 2I plus b0 over 2 minus a0 over 2I plus b0 over 2. So this is 0th term plus this thing. But now since 0th term is gone, this is going to be start from 1. Plus, let me shift this just a little bit. Again, this is n is equal to 1 to infinity, this term. Now here in this one, I want to change the variable from n to minus n. Okay? And that means I can go from n is equal to minus 1 to minus infinity. Actually, typically we need to write it from lower bound to upper bound, so let's write it like that. Minus infinity to minus 1. Since I put n is equal to minus n, I can just write here minus n. Okay, let me use a different color. So this is an became a minus n, bn became b minus n, and here I have minus n already, so I'll erase this. Now I want to define a, okay, let's also cancel this. I want to define a new coefficient. Let me call this Cn. What is Cn? Cn is equal to, so b0 over 2 plus b0 over 2, b0 if n is equal to 0. And I want it to be an over 2I plus bn over 2 if n bigger than 0. Let me actually write it a little bit more explicitly. If n is equal to 1, 2, 3, dot, dot, dot. And this thing if n is equal to -1, -2, -3, dot, dot, dot. Good. And then I can write f of x as, now n goes from -infinity to +infinity, some Cn e to the I n pi over a times x. Right? We had the Fourier series, it was written in terms of sines and cosines. By combining the coefficients, we write it in terms of exponentials. Now, I want to write Cn in terms of f of x using the Fourier tricks. So now what we are going to do is multiply both sides with e to the minus I m pi over ax and integrate. That's the Fourier trick. So multiply with e to the minus I m pi over a x and integrate from minus a to a dx. So the left hand side is simple, minus a to a dx f of x e to the minus I m pi over ax. Right hand side is equal to, again, minus infinity by minus a to a dx. I'll copy this entire thing and e to the minus I m pi over a x. But now I look at this integral, right? This integral is x integral, and the only x-dependent object here is this. So let's then take the integral. So minus a to a dx. I'll combine these exponents, e to the I n minus m pi over a times x. Let me write it here. This thing is equal to, if n is equal to m, this is 0, and right, and the integral is immediately to a. If n is equal to m, there is no simpler integral than that. Otherwise, we have to take the integral e to the I n minus m pi over a x divided by I n minus m pi over a, and the limits are from minus a to a if n is not equal to m. Since this is valid for n not equal to m, I don't have any denominator problem. Nothing is blowing up. Now let's look at this expression. So this is e to the I n minus m. If I put a is cancelled, this is pi minus e to the minus I n minus m pi divided by I n minus m pi over a. And this is going to be equal to 2i sine n minus m pi divided by I n minus m pi over a. What is this? Sine integer times pi. This is 0. Therefore, this integral we can write as delta n m. Right? If n is not equal to m, it's already 0. But if n is equal to m, it is 2a. So let's also write 2a. So this one, why is this 0? This one? Because sine 0 is equal to sine plus or minus pi is equal to sine plus or minus 2 pi. They are all 0. Right? Therefore, let's go back to right hand side. Right hand side. Yes. Yes. We know that, but even if we didn't know, we could see it from the integral. Now, so this is n is equal to minus infinity to plus infinity. This is Cn. And we took the integral, so let's put it. So this is delta n m times 2a. But we know we like this, right? Because this is going to pick up the coefficient we want. So this is going to be Cm, and summation is gone, right? This delta function, Dirac delta or Kronecker delta, and this summation, they are going to kill each other. That means this is Cm times 2a. And right hand side is equal to left hand side. And left hand side is this. From here we have an expression for Cm. So this is Cm is equal to minus a to a dx over 2a f of x e to the minus I m pi over a times x. Now, even if we started with these exponentials, right, we could also see that this is e to the I kx kind of solutions. This is also a solution of Schrödinger equation. And if I require periodic boundary conditions, e to the I k x plus 2a is equal to e to the I kx. This immediately gives me k times 2a is going to be 2 pi times n. And this is exactly the condition for this m pi over a. Right? I could also start from these solutions and get to this result without the Dirichlet's theorem. But now what I want to do is, like, I want to take the limit a goes to 0 and see how this thing turns into Fourier transform. We go from Fourier series to Fourier transform by taking the limit a goes to infinity. So what I want to do is, like, so n is the variable, I want to change this variable with n pi over a, and I want to identify this with k. And as a goes to infinity, k will be continuous. And you can see delta k, the distance between two different values of k is going to be pi over a. So let's do this. So this is f of x is equal to, so n, I'm not writing minus infinity to plus infinity anymore. So this is delta n is 1, right? N, the distance between two different k values, n plus 1 minus n is 1. So there is 1 here. These are discrete values. But as a goes to infinity, delta k goes to 0. So this is Cn. This is e to the I pi over a and x. I didn't do anything. I rewrote the same expression. So what I want to do here is, let's copy and see how I manipulate. So I want to put delta k over 2 pi and 2 pi over delta k. Why delta k over 2 pi? This is going to be dk over 2 pi, then that's what we had for Fourier transform integrals. Now identify this thing with, because n will go to n times pi over a identified with k, I'm going to identify this with f of k. So I multiplied, so this is, okay, let me do it the other way. I multiplied and divided it with the same thing. Because if you remember, we defined Fourier transform like this, right? dx over root 2 pi, dot, 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 and dk over root pi. At least this is what the book does. I personally like this formalism better, right? I've been taught to have dx alone and dk over 2 pi, but the book is using this convention, and that's okay.
No difference.
There's no difference. You can like relabel the functions and it's the same thing. Just make sure which definition you are using and be consistent. So that's why I'm trying to put this summation will be integral in a little bit, and I need this dk over 2 pi. That's why I have this here. Now this thing, I identify f of k. This thing, I'm going to identify it with dk over 2 pi, and this thing, I'm going to identify this with e to the I k x. Is that okay? And as a goes to infinity, this thing is going to go to an integral minus infinity to plus infinity. This is dk over root 2 pi. This is fk, the Fourier transform, and this is e to the I k x. Actually, let's write an equation. So this is f of x. And let's do the same thing with the inverse. So this was the expression. Well, let me use n, because what we use above, this is n. And what I want to do is I want to multiply, because you see f of k multiplied with root 2 pi over delta k. Let's do the same thing here. So this is root 2 pi over delta k. And if I multiply it here, I need to do it also here. Let me push it a little bit. This is root 2 pi over delta k. And let me also write what delta k is. Delta k is pi over a. So this thing, as a goes to 0, this thing is going to be f of k. As a goes to infinity, and this goes minus infinity to plus infinity. You can see this thing and this thing cancels. root 2 pi divided by 2 pi is root 2 pi. So this is dx divided by 2 pi f of x. And this thing is going to be e to the minus I kx. So I want to do one more line of calculation and use that calculation to show you Parseval's theorem, and we can take a break after that. So let's go back to this result here. Right, this blue line, you can see this integral is going to be some Kronecker delta, but let's use this line. Because now I want to insert a, and I want to take the limit a goes to infinity carefully. Now, consider orthogonality, and we want to go from Kronecker delta to Dirac delta as we go to a goes to infinity limits. So this is minus a to a. So this is dx e to the I n minus m pi over a x. What we found there is, let me write the result, e to the I n minus m. So I want to write it like this, pi over a. Because k is defined in terms of n pi over a, I have to put back a, and I do this, minus e to the minus I n minus m pi over a times a, and divide this entire thing with I n minus m pi over a. So what I will do is I'll identify k with n pi over a, k prime with m pi over a, then this thing, and I'm going to take the limit in a little bit, this thing is going to be sine k minus k prime times a, right? So there's k minus k prime from here, and this whole thing, okay, there's also 2 because there are 2, and i's are going to cancel, and this is divided by, this is k minus k prime. So as an exercise, there is like a limit expression, and this expression will then generally come to us when we are dealing with Fourier series and things like that. Let me just write it and ask you to convince yourself this is the case. So the limit a, there are different forms, but I wrote it like this in our case. 2 times sine k minus k prime a divided by k minus k prime. Does anybody know what this is? Actually, let's write. Typically, if you look at, for example, Mathematica has an expression for this, and sometimes they also put pi here. Yes. We wrote which one? Oh, it is like this. Yes, thank you. It is like this. So it is argument of sine. Yes, thank you. Does anybody know what this expression, this limit is? We see this a lot in calculus. 1. What if k is not equal to k prime? So this is delta. Let me write it in like a more there's like an easier way to see this. I think let me write it like this. Alpha x divided by pi x, and the limit alpha goes to infinity. So this limit. Like you can look at your books and this is going to be delta of x. Okay? And this means this object, right? I have like a 2 here and I have like a missing pi. This object will go to 2 pi delta of k minus k prime. So if you want, here's your exercise. Prove above Dirac function. Dirac delta function. So what you need to do is there are like 2 things you need to prove. The first thing, so if you call this limit g of x, what you need to do is you need to first show that if you integrate from minus infinity to plus infinity dx, g of x, you need to show this one by playing with limits. And the second thing you need to show, if you go from minus infinity to plus infinity dx, g x minus x0, f of x is equal to f of x0. If you want, you can also take x0 is equal to 0 and show it. And if you show these 2 things, you immediately prove this thing I wrote to you. Okay? But let's come back to what we have here. Like here we have minus infinity to plus infinity. So this is, you can see dx e to the I k minus k prime x is equal to 2 pi delta of k minus k prime. Okay, one last hit because we started a little late and then I'll finish that. So it came from this limit expression. So if you do this exercise I and double I without pi, you are going to find pi here. And if you take this integral, right, if you integrate this expression from minus infinity to plus infinity and take the limit outside, I did it even with Mathematica that gives you the correct pi. But generally textbooks put pi here and write delta alone.
We say that x, we have a Dirac function of x, right side, but in the former expression we have the function of k minus
yes.
k prime.
If you have this x, you can write it like y. This is for any variable, right? X and y are dummy variables. So this is y, and this is going to be y. So if this is valid for y, you can substitute y is equal to k minus k prime, and it's also valid for that. Right? X, y, k minus k prime, these are dummy variables. Wherever I see k minus k prime, I can write y and use this expression. A little confusing, but yeah, it's...
So we identify y as k minus k prime.
Yes. And the limits, we are also identified alpha with a and k minus k prime with y, and use this expression. But independent of all the calculations we did today, you can just sit down and play with this expression to see these things. This is a standard exercise in mathematics books, so you can also look at that. Okay, let me do one last thing and then I'll finish it there. So what did we learn? We learned f of k, so this is the Fourier transform, minus infinity to plus infinity, dx over 2 pi f of x e to the minus I kx. Now I want to take the complex conjugate of this thing. So this is f star. I'll have f star here, and this one is going to be plus. And because x is integration variable, not to mix up. Let's put like a x prime here, right? X prime, you can put y, whatever, because it's integrated over anyways. Now let's multiply it side by side. On the left hand side, what I have is f of k squared is equal to, on the right hand side, I have minus infinity to plus infinity dx over 2 pi minus infinity to plus infinity dx prime over 2 pi. Okay, this is also x prime. I have f of x, I have f of x prime, and I have e to the I k x minus x prime. Good. And now I integrate both sides. Yes, thank you. So this is x prime minus x. Thank you. Now I integrate both sides. Let's integrate. Let me copy. And integrate dk. And I need to do the same thing here, but you can see this entire blob, there is nothing k dependent here. So let me make it blue for you to see easily. Right, there is nothing k dependent here. So my integral can jump all the way and I can put it here. So this is dk, my infinity to plus infinity. But we found an expression for this, right? E to the dx k minus k prime 2 pi, and exactly the same thing. The only difference is, right, these are dummy variables, dummy labels. I can just write here exactly the same expression here. This is 2 pi delta x prime minus x. Now, this 2 pi is going to cancel these two. And this delta function is going to kill one of the integrals. And at the end, what I have is dk f of k squared is equal to dx minus infinity to plus infinity minus infinity to plus infinity f of x. Oh, there is also one star, right? I forgot this f star. So there is this star, this star. So this is f square. And that's how we obtained, I think, what did we call this? Parseval's theorem. Good. Any questions? Right, let's take a 5-10 minute break and continue.